What are gravitational waves? I'm sure that at some time you've heard about the typical explanation about gravity, but if you haven't, here it is. Try to picture an elastic surface. Now place an object on it. As you will be imagining, the surface you thought about has just curved. Now, although this explanation seems great, it is a good way to illustrate it, but the truth is that it doesn't make things perfectly clear. We know that space-time is not a giant trampoline, so why is it curved? To graph the space, we use three dimensions: length, width, and height. But now we are going to turn all these three dimensions in one dimension called space. Now we are going to graph space and time. If we released something in space, it wouldn't move, so we will stay on the same value of space axis. However, it will move through time. But if an object moved at a constant speed, it would move on the space axis and on the time axis, so we would get a diagonal line. If a body's energy curves the fabric of space-time, lines still straight, but space-time is curved. Therefore, from our perspective, it is the lines that curve. Now we've got an idea about what gravity is, but this is what we wanted to talk about. What are gravitational waves? Gravitational waves are the disturbance in the fabric of space-time generated by accelerated masses. These waves propagate at the speed of light. Let me give you some examples. If an extremely massive body was moving tremendously fast, it would happen something similar to what happens when we put our fingers in water and move them. As you can see, this produces waves in the water, which can be used to picture gravitational waves curving the fabric of space-time. Here you can see a two black holes collision simulation, generating waves due to their masses and the speed they are moving at. As you may see, it's pretty similar to what I showed you before. Do these waves exist? Sure they do, but how do we know? Welcome to LIGO. LIGO's mission is to open the field of gravitational waves astrophysics through the direct detection of them. How does it work? Basically, what we have is a laser. This laser fires out a beam of light, which is sent through a partial mirror at 45 degrees. Some of the light will be reflected this way, and the rest of the light will continue following a straight line. At the end of each of these two channels, we've got a mirror that will make light come back. As their wavelengths are antiphase, they will cancel each other. But when a gravitational wave reaches the Earth, there are some little disturbances in the fabric of space-time, which affect the distances we can measure in these tubes. That's why these two beams will stop being antiphase. So they will stop cancelling each other, letting some light pass and finally reaching the light detector. Detecting gravitational waves is very important. It's an entirely new way to learn about the universe. Scientists' job is now to dream big. Let's dream with them.